So there's sort of something exciting to me about just seeing this process of mathematicians trying to come up with the most concrete problems they are capable of and challenging both each other and machines to solving them. There are a couple reasons that Epoch AI has chosen to put all this effort into building a math benchmark in particular. One of which is that mathematics is a completely objective discipline. In all of the problems we are producing, there is a unique or otherwise objectively verifiable answer that can be automatically verified. Now, as for why one should care about AI's ability to reason in math, particularly, in my view, one of the big bottlenecks regarding AI's development in reasoning in general is their ability to come up with a coherent, consistent worldview and a consistent notion of truth, and also to engage in long form successive reasoning regarding truth. So we feel that AI's ability to solve math problems is a good proxy for its ability to reason in this sort of problem, even in the far more general context of the real world. The current bottleneck in a lot of LLM models in particular is that they engage in a lot of ad hoc pattern matching to come up with what they say, but this is all very different from actually having some concept of belief or truth. So I don't think that the kind of problems we have produced, especially at the upper end, is going to be solved purely by scaling up the current LLMs. I think that the kind of paradigm that has a solid chance at beating this benchmark is something that relies much more heavily on an internal objective client, either something like a formalized proof assistant like Lean, or perhaps some sort of internal analog of the way humans engage objectively with mathematics. And once they have such a client in store, then they can use the techniques that they've used to build, say, the elite chess and Go models and apply that within to efficiently search for new proofs within that system. There are multiple difficulties in trying to get LLMs to be able to solve these problems purely by training on the available data. For one, every math problem is an essentially original, precise entity. Even if an AI is able to train on similar topics found within research papers or in textbooks, even a slight change in the wording of a math problem can actually very fundamentally alter the underlying mathematics in it. So it would not be able to simply guess at the answer by looking at the publicly available data. And another problem with just relying on what has been publicly written about mathematics is that really only covers a tiny fraction of the mathematical experience. Every mathematician on the process towards solving whatever problems they're working on they encounter lots and lots of failure. Like, I'd say that in my own research, 95% of the ideas I've had for how to tackle something have went nowhere. And mathematicians aren't particularly keen on talking about these dead ends or talking about how they came up with all the epiphanies they did to finally reach a solution. In fact, a lot of us basically pride ourselves in covering up our tracks and coming up with these papers where it seems like the key steps that we did to solve the problem just come out of nowhere and are magic. The actual pedagogy of learning how to do mathematics properly is mostly acquired through conversing with our fellow mathematicians or talking to our advisor in grad school. So there is so much of the experience of becoming a proper mathematician that I don't think LLMs really have access to simply by training on internet text. The current viewpoint of my colleagues and I is that this benchmark, at least as it currently exists, will last about 5 years. That being said, we're still acquiring new problems, and we will continue to do so throughout the year. And we are actively seeking out problems at the highest end of the difficulty range. So my opinion is that when the data set is finalized, it'll be a fair bit more difficult than what we currently have, and that it will last even longer than that. I think the problems on the FrontierMath benchmark dataset they have a lot in common with research math problems, or at least definitely more so than the sorts of Olympiad problems that have been used in prior benchmarks. They definitely cover all the major fields of mathematics. To begin tackling them, you have to have at least a researcher's understanding of the field. That being said, there are definitely still gaps between our hardest problems and the most difficult research projects faced by actual professional mathematicians. Even our most difficult current problems are designed to be solved within at most a week of effort, while professional mathematicians will often spend literal years on a single math problem. So while I think an AI that solves our hardest problems will be pretty close to professional researcher level, there is definitely still a gap that they would have to cross before we can truly say that they have utterly mastered the human art of mathematics. Another thing that separates the frontier math benchmark problems from a typical research math problem is that virtually all research mathematics is proof based. It's about coming up with proofs for various conjectures that have been posed within the community or our own problems that we have come up with to further our research agenda. While on our benchmark, all the problems have closed form solutions, usually integers, sometimes tuples of integers or symbolic real numbers, but always closed form solutions. And while this is the norm in math contests, it's definitely not the norm in research mathematics. So, as I've gone through the process of making my own problems, or as I've talked to other mathematicians and explained to them the process by which we make these problems, we've all had quite a bit of a struggle trying to convert our proof based agendas into this very constrained format. Difficulty with trying to get math problems in the benchmark that cover the broad range of mathematics is that some fields are more suited for this kind of numerical form than others. Like, we haven't had too much difficulty getting number theorists, graph theorists, combinatorialists to come up with very concrete integer based problems. But for other fields, like my own, set theory, well, these are very abstract subjects, and in our own research, it's pretty rare for us to ever encounter any whole numbers that aren't one digit long. Well, let's talk about an issue on the other side of the coin, which is once we get problems, how do we verify them? Well, we do have a team of reviewers, all of whom are very competent mathematicians, and we always try to assign problems to mathematicians who are qualified to examine them. And we're always perfectly willing to accept if a reviewer says, I can't handle this problem, it's not my field, try giving me to someone else. But there's another issue that makes these problems particularly hard to review, which is that most mathematicians, when looking at each other's research, they tend to care more about the big ideas and concepts that have been revealed by their research agenda rather than the nitty gritty. It's a bit of an open secret in the math community that most papers have errors in them. Usually tiny errors that don't change like the major theorems that are headlining the papers, but tiny little errors scattered throughout nonetheless. And that doesn't really collapse the mathematical apparatus of our community. But it's definitely a problem whenever that happens with our problems. If a problem is missing a minor hypothesis, or if there's like a slight miscomputation in getting the answer, well, how then are AI models possibly going to get the answer we have officially put into it? So, our problems need to have a higher level of scrutiny than mathematicians usually give when engaging in the peer review process. And this is a difficulty we are still working on overcoming, but we are largely trying to switch right now from a passive reviewing process where we simply ask reviewers thumbs up or thumbs down to one that's more active, where instead of actually giving the reviewers a solution to the problems, we're only going to start only giving them the general framework, the concepts that the author says were actually needed to solve this problem, maybe an outline of the techniques and the steps to solving the problem, but we're not actually going to give the reviewers the solution. And if they do solve the problem themselves and they get the exact same answer as was given by the author, that is much stronger evidence of the correctness of a problem than them merely looking over a fully written solution and saying, yep, that's good. We have found that it's harder to get hard problems. I suppose that shouldn't be very surprising, but it takes a lot of effort to make a really hard math problem, especially since it is a requirement of our authors that they provide fully written solutions that can justify to another expert that their solutions are correct. So this requires a lot of effort, and it also requires us to seek out very talented mathematicians to contribute to our project. One of the challenges with developing this project is coming up with a reasonable scale for assessing the difficulty of the problems we receive. Right now, we are using a 3-axis scale for measuring difficulty of problems. One, the background knowledge required to even understand the problem and the concepts needed to solve it. Two, the level of creativity needed to figure out the key steps to solving the problem. And three, the amount of computational labor it requires to precisely work out the answer once you understand the general approach to the problem. So we have found this to be a fairly good system for breaking down the difficulty of a problem, but it still suffers from being somewhat subjective. And we have found that our internal reviewers have disagreed with each other regarding ratings of the problems. So we are working right now to come up with a better normalized system so that we can assign rather canonical ratings to these problems. And then once we have ironed out that system, the next step for us is to figure out how to convert these ratings into a prediction regarding how long it will be before AI models are able to solve this problem, at least on a relative scale. Even if we don't really have a good prediction regarding how fast AI models are going to improve their mathematical reasoning, we'd like to at least have a relative ranking of how long we expect each problem to last, which ones will be the last ones to fall to AI models. One of the big ways in which the FrontierMath project has evolved from its original conception is our increasing emphasis on the higher ends of the difficulty scale. So in the original version of the project, we intended to make problems covering quite a large range of difficulty. But as we looked at the rate at which AI models are improving, and looking at how much each successive model has improved over the previous ones, we quickly realized that the lower ends of the scale that we were originally considering using would get solved pretty fast. And we didn't want to have it to be the case that a large percentage of our benchmark would get saturated within just a few months of release, if not prior to the project even being finished. So we have since focused more on the higher ends of difficulty. For the most part, we nowadays only accept problems that we think will last at least a year, and ideally much larger than that. And as we approach the end of the project, most of our resources at this point are on recruiting authors and mathematicians who we believe can provide us problems at the higher end of the scale, problems that we feel will last up to 5 years from now, if not even more. There are a couple things about this project that are particularly exciting to me as a mathematician. I'm a set theorist, and most of my research is in the field of metamathematics. I look not just within a single formal mathematical system, but many, and compare what it is like to prove problems in one system versus another, as well as how difficult it is, or what are the lengths of proofs in various systems. And one interesting thing about then trying to understand the relationship of math and artificial intelligence is that in some sense, this gives us a more objective sense of where mathematical difficulty comes from, seeing how long it takes for a precisely defined machine to solve problems versus the more subjective nature of human mathematical reasoning. So as this project evolves, I have been excited to see the insights it has given into the nature of mathematical difficulty itself. And another thing that I've enjoyed about this project that I actually didn't expect to enjoy going in is all these constraints that come from the purely numerical forms of these answers. In math contests, it is the norm for problems to have a simple singular answer as opposed to coming up with a long form proof of a problem. Me and most of my colleagues tend to be dismissive of this form of mathematics. I'm starting to realize there's like a refreshing honesty to it, in that there's something really honest about proving that you are good at math simply by answering concrete questions with a concrete end. Mathematic research has gone so specialized. Most specialists just aren't even able to understand the theorems that their colleagues produce if they are not within the same subfield as they are. So there's sort of something exciting to me about just seeing this process of mathematicians trying to come up with the most concrete problems they are capable of and challenging both each other and machines to solving them.